As one of the good practices to inculcate research activity and scientific discussions among our students, I'm very happy to welcome you to the second lecture in the students webinar series, which will be delivered by Dr. Ashadul Halder. Dr. Ashadul Halder has recently completed his Ph.D. degree from our esteemed institution under the guidance of Dr. Shivaji Banerjee. This is a forum is to encourage our students to talk about their work and studies. I sincerely hope with your active participation along our students and colleagues, this will evolve as a great platform for the scientific discussion and activity. I hope we shall continue the webinar series maybe in the online or offline in future depending upon the situation. I want to thank all my departmental colleagues and students for their active support always for the academic excellence of the department. Now, I request Dr. Shivaji Banerjee, who guided Ashadul, to introduce him and conduct the question answer session, and at the end, deliver the vote of thanks. Over to you, Dr. Banerjee.
Thank you very much, Indra. So, today is my interesting and pleasant task of introducing Ashadul to the rest of us. Now, when I asked him for some data on himself, he wrote me back just 3 lines about himself. Now, these 3 lines tells us that he has done all his schooling in Naktala High School and completed his BSc degree in Physics Honours from Dinabandhu Andrews College affiliated to the University of Calcutta. Now, this data just shows that he is very deeply rooted in South Calcutta, and later evidence showed us without reasonable doubt, in fact, without any shred of reasonable doubt, that he loves his folk so much that he never wishes to move out of that corner in the world. Now, Asadul subsequently joined our college for MSc, and before completing his degree, he has constructed an experiment using lunar terrain photography. This experiment has now become a staple in the astrophysics lab. Now, after slipping through most of my classes in MSc, he decided to join me for PhD. He came with a CSIR scholarship, and nothing I could ever say would dissuade him, so he got his wish. Now, during his slightly less than 5 year stint, he devised experiments for the UG lab using interfacing techniques, built an entire virtual lab for the GE students during the lockdown period, and worked on little inventions which might someday rightfully derive a patent. This is regardless of his efforts handed in for the smooth running of the departmental events and contributing related artwork. His research spanned a wide zone in the area of astroparticle physics, which are mostly concerned with the identification and role of dark matter candidates in various astrophysical scenarios and semi-analytical models of rotating compact stars. But about that, he will talk about in his lecture. Ashadul completed his PhD in this year with a big set of publications and an elegantly written thesis. He is in fact the first to come out with a SXC degree from the Department of Physics. May Father Lafu and the other stalwarts of the departments bless him. If Professor Gomes and if Professor Diembos have been here, they would have been very much delighted, or maybe they are. During his tenure as a PhD student, he successfully collaborated with scientists from Bose Institute and SINP. I regard Ashadul as an hacker scientist do-gooder, and he's an example of a pure and warm, gentle human being, very shy about shouting his accomplishments out, and always inclined, in fact, on his toes to help whoever is in need for it. All the best for his talk and the listeners, and handing it out to Ashadul. Stage is yours.
Thank you, sir. Good afternoon, everyone, and thank you for attending my presentation. Today, I shall discuss an elementary idea of dark matter and 21 centimeter cosmology. Current cosmological paradigm tells that a very tiny percentage of the entire energy budget of the universe belong to the ordinary matter, that is around 4.9%. The remaining unseen part is essentially distributed among the two dark sector components of the universe, namely dark matter, which is around 26.6%, and the currently dominating part, dark energy, which occupies around 68.5% of the total energy budget of the universe. Today we shall discuss about dark matter, which is 26.6% of the universe and around 84.34% of the total matter. The remaining 15.66% 66% matter exists in the form of visible baryonic matter. Whatever we can see in the sky, that is stars, planet, nebula, etc., all of those belong to this tiny part, 15% of the matter, which is while the major part, that is dark matter, is still unexplored. Famous British mathematical physicist Lord Kelvin was among the first to attempt dynamically estimate the amount of dark matter in the Milky Way. In 1884, Lord Kelvin commented about the unseen dark celestial object in a conference talk. His argument was simple yet powerful. If star in the Milky Way can be described as a particle of gas acting under the influence of gravity, then one can establish a relation between the size and the system of the velocity and the velocity dispersion of the star. Later, Henry Poincaré termed those dark objects as dark matter in his book The Milky Way and the Theory of Gas, which was published in 1906 in French. After that, several observational evidence has been detected that justify the conjecture of dark matter. The idea of dark matter is still well motivated in the framework of cosmology and astrophysics. Several astrophysical observational favors the existence of dark matter, which are essentially based on the gravitational effects. Here we summarize some few most compelling pieces of evidence of dark matter. Flattening of the galactic rotational curve of the spiral galaxies is one of the most promising evidence for the existence of galactic dark matter. In the year 1975, famous American astronomer Vera Florence Cooper Rubin, or known as Vera Rubin, brought into light his sensational fact. Are you sorry? She investigated the rotational curve of several spiral galaxies and obtained remarkable discrepancies with the calculated curves, which are estimated by incorporating only the visible part of the galaxy. After their extensive studies, the availability of galactic dark matter is universally accepted. Although in 1959, another astronomer, Louis Baldors, also pointed out the identical discrepancies beforehand in the case of M33 galaxy. The rotational curve describes the variation of the circular velocity of the star and the interstellar medium ISM with the radial distance of the from the center of the spiral galaxy. The velocity can be estimated by measuring the Doppler shift of the hydrogen spectra. Tracking the motion of the star around the galactic center is another significant method in measuring the circular velocity at a particular radial distance from galactic center. According to the classical theory of gravity, the stars revolve around the galactic center, keeping the centrifugal force equal to the gravitational force. From this, it can be estimated that the circular velocity v should proportional to r within the central bulk. On the other hand, outside the central bulk of the galaxy, the velocity varies with r as v proportional to 1 by root over r, as we can see in this yellow dashed line. However, the observational evidence indicate that V proportional to R to the power n, where n approximately 0 or slightly greater than 0. As a consequence, there must exist an additional invisible matter distribution which induce the nature of the this rotational curve. This invisible dark matter is believed to exist in the form of dark matter halo. The density profile of galactic dark matter halo can be estimated by accommodating the nature of the galactic rotational curve as obtained from the observational evidences. The gravitational lensing is another promising probe in the detection of dark matter in intergalactic medium. The notion of the general theory of relativity tells that the light follows the curved trajectories as described by the geometry of the space in the vicinity of massive object, as shown in this figure. As a result, the observer may see the distorted and multiple images of light source, which is actually situated beyond the massive lensing astrophysical bodies. This phenomena is known as gravitational lensing of light. The concept of the lensing by a massive astrophysical object was first proposed by Henry Cavendish in 1784 in his unpublished article. Later, in 1915, Albert Einstein successfully calculated this phenomena in the context of his famous theory of relativity. On 29th May 1919, Eddington and Dyson confirmed Einstein's prediction using their famous observation. It was the first observational evidence of gravitational lensing. The effect of gravitational lensing can be classified into three categories, namely microlensing, weak lensing, and strong lensing. In the case of microlensing, only the intensity of the background stars increases apparently, and this phenomena can be observed using this bright spot, while the weak gravitational lensing manifests a slightly deformed images of the background source. For example, this deformed region. On the other hand, the effect of strong lensing is easily observable in the form of Einstein ring or multiple images. In general, the strong lensing generates multiple images of the distant object. However, in some special cases, the lensing object and the observer are perfectly aligned to the distant object. In this case, the lensed image looks like a ring, which is known as Einstein ring. That can be seen in this figure. Bullet cluster is another convincing example of dark matter. Almost 4 into 10 to the power 9 light years away from us, a striking piece of evidence of dark matter has been observed as a bullet cluster. The bullet cluster is basically two colliding subclusters located at the Carina constellation. However, in several cases, only the smaller subcluster is considered to be the bullet cluster. The observations describe that during the high velocity collision with 4,500 km per second between these two clusters, the shape of the baryonic mass distribution perturbs significantly, which is described using these pink parts, while the dark matter halo pass through each other undistorted, which is shown here using blue parts. It is to be noted that the invisible mass dark matter halo for the two clusters are identified by the method of gravitational lensing. This shows that the dark matter particles do not have any interaction except the gravitational interaction. Therefore, one can conclude that a significant amount of dark matter present in the blue zone, which is responsible for the gravitational lensing. This is also strong evidence for non-interacting dark matter. An identical phenomena is also seen at the MACS J0025.4 minus 1222 cluster. Depending on different aspects such as production mechanism, particle nature, etc., dark matter can be classified into different classes. And depending on the velocity during the structure formation, the dark matter candidates are categorized into 3 groups, while the dark matter candidate can be sorted in 2 groups based on the baryonic nature and their production mechanism. At the time of structure formation, some dark matter particles move with relativistic velocity. Those relativistic dark matter candidates are termed as hot dark matter. Hot dark matter are characterized as xf equals to m chi by tf, which is greater than equals to less than equals to 3. Here m chi is the mass of the dark matter particle and tf is the corresponding freeze out temperature of those candidates. Consequently, dark matter candidates are comparatively lower in mass. Massive neutrino belong to this category of dark matter. Observations of Lyman alpha forest, Planck, WMAP impose significant constraints on hot dark matter. Massive neutrinos, axions, etc., low mass particles belong to these categories of dark matter. The cold dark matter candidates are characterized by XF greater than equals to 3. Consequently, they are comparatively cool and non-relativistic during structure formation. Such candidates of dark matter are highly contextual in cosmological large-scale structure formation. One of the most popular candidate of this class of is weakly interacting massive particle or WIMP, which is studied extensively in the context of beyond standard model particle physics. However, few discrepancies are observed between theory and observational result, namely missing satellite problem, too big to fail problem, core versus cusp problem, etc., which cannot be explained using these 2 categories of dark matter. As a consequence, a third category is introduced, that is warm dark matter. Warm dark matter are the intermediate dark matter candidate, which is less relativistic than hot dark matter and more than cold dark matter. In this case, the factor xf is almost equal to 3. Such candidate of dark matter are assumed to decoupled at the temperature T much greater than TQCD. So the mass of warm dark matter particle is almost 10 times more massive than hot dark matter particles. Dark matters can also be categorized into 2 different classes based on the nature of their constituents. One is the baryonic dark matter. Being baryonic in nature, MACHOs, that is massive astrophysical compact halo object, black holes, neutron star are considered to be the candidate of baryonic dark matter. The nature of the galactic neutron stars are considered to be the candidate of the nature of the galactic rotation curve indicates that the galactic halo are enriched with such massive dark matter candidate. The detection of several microlensing events in large Magellanic cloud is possibly another significant evidence of baryonic dark matter in the Milky Way galaxy. As the fuel of a white dwarf runs out, it cannot radiate and hence cannot be observed directly anymore. So an exhausted white dwarf star can also be considered as baryonic dark matter. Moreover, primordial black hole, brown dwarf, etc. can be included in this category of dark matter. Actually, the density of the visible matter can be obtained from the mass to luminosity ratio. The star satellite-borne Planck experiment in accordance with COBE and WMAP estimates that baryon temperature, which is roughly the same as obtained from the mass to luminosity ratio. The bounds on the baryon density calculated from the BBN, I mean Big Bang nucleosynthesis theory, also agrees with those estimations. So there is not much room for such dark matter candidate except galactic gas, intergalactic gas, and non-luminous stellar objects. The second one is non-baryonic dark matter. According to this recent Planck result and CMB spectrum, the total amount of dark matter containing the universe is several times larger than that of the total baryonic mass. As a consequence, there is only a very small percentage of dark matter exists in the form of baryonic matter, while the almost entire dark matter population is non-baryonic. Such kind of dark matter interact very weakly with standard model particles. As a result, direct detection of such dark matter candidate is extremely difficult. Most of the candidates of non-baryonic dark matter are extended standard model particles, supersymmetric particles, Kaluza-Klein dark matter, which is inspired by extra dimensional theory, Wim-Zillers, super heavy dark matter decay, axion, etc. Some plausible candidate of non-baryonic dark matter. According to the production mechanism, dark matter can also be classified into thermal dark matter and non-thermal dark matter. Initially, thermal dark matter candidates were assumed to be in thermal equilibrium in the early epoch of the universe. Later, as the temperature and hence the interaction rate decreases as the outcome of the expansion of the universe, they started decoupling from the cosmic plasma. WIMPs are one of the notable candidates of such dark matter candidates, which are assumed to be in thermal equilibrium when the universal temperature was sufficiently high. WIMP means weakly interacting massive particles. After being decoupled, the created pairs of particle-antiparticle can also undergo annihilation and hence produce supersymmetric particles. Initially, those two particles were in equilibrium, but as the expansion rate of the universe dominates over the particle-antiparticle annihilation rate, the number density in the co-moving volume freezes. This density of the dark matter after freezing out is known as the relic density, and corresponding temperature terms as the freeze out temperature of that particular dark matter species. The relic density of such thermally decoupled dark matter candidate depends on its annihilation cross-section, while the non-thermal candidate of dark matter are thought to be produced from oscillating pseudoscalar fields or produced gravitationally. As the pre-BBN, I mean Big Bang nucleosynthesis cosmic history is still unknown, it is possible that some heavy dark matter masses of 10 to the power 5 to 10 to the power 16 GeV candidate can be produced gravitationally in the post-inflationary epoch. Wim-Zilla is such a candidate of non-thermal dark matter. Moreover, axion and axion-like particles, which is known as APL, are other example of non-thermal dark matter. Although at a higher temperature, axions are almost massless at the QCD scale, the mass of the axion hovers near the minima of the axion particles, that is less than 10 to the power minus 3 eV. Dark matters cannot be observed directly as they do not interact with electromagnetic field like other visible baryonic elements. As a consequence, beside particle dark matter, namely WIMP, just a minute, namely WIMP, axion, etc., several kind of non-luminous astrophysical objects like macho, brown dwarf, pure quark star, etc., are also considered as dark matter candidate. The mass range of different types of dark matter are addressed graphically in this figure. The weakly interacting massive particle WIMP is the leading candidate of dark matter, lies in the range of 2 GeV to up to 10 to the power 5 GeV. Wim-Zilla is a comparatively heavier dark matter candidate, which is probably originated in the post-inflationary epoch. The Wim-Zilla are considered as a part of wider group that is super heavy dark matter or heavy dark matter. Super heavy dark matter may come with mass range of 10 to the power 6 to 10 to the power 16 GeV. Moreover, there are few alternative model of dark matter indicating the evidence of right-handed neutrinos, axions, axion-like particles, etc. are dark matter candidate. These dark matters candidates are comparatively lighter than other candidates of dark matter, which are less than 1 MeV. On the other hand, primordial black hole, machos, pure quark star, etc. astrophysical objects are also believed to be dark matter due to their extremely low luminosity. The maximum mass of such astrophysical bodies are in the order of stellar mass. This paper was published in MNRS in 2020. In this work, we considered two particle dark matter models and studied their phenomenologies. We calculate the gamma ray flux from the self-annihilation of the dark matter within this framework for all 45 dwarf spheroidal galaxies, which are considered to be dark matter-rich celestial objects, and then compared the computed result with the observational upper bound obtained by Fermi-Lat and dark matter energy survey for each of them. These flux were calculated. These flux were calculated by adopting different dark matter density profile. We then extend similar analysis for the observational upper limit given by Fermi-Lat for the continuum gamma ray flux originated from extragalactic sources. In this publication, we constrain the mass as well as the decay lifetime of super heavy dark matter candidate using the detecting upgoing muon neutron events in the PeV energy range, which was detected by IceCube experiment. Beside dark matter and dark energy, the evolution of the universe in the dark age is another mystery of the astrophysics and cosmology. The dark age started subsequently after the end of recombination in the early age, that is 370,000 years after the Big Bang. Initially, the universe was opaque. Everything in the universe was enveloped by a fog of neutral hydrogen. But during the recombination, the universe became cool enough, the electron starts freezing out at some small region. Therefore, those small region become transparent. Then those small transparent region grows over time as the temperature of the universe decreases and eventually occupy the entire universe. Although the universe became transparent, there was no significant source of light in the universe. So the universe was dark during that epoch. It is the starting of cosmic dark age. Although initially the universe was filled with pale orange glow of cosmic background, it redshifted to non-visible region after some time, that is around 3 million years after. It is assumed that at that time the universe was filled with gas, dust, and floating rocks. But the dark age did not last forever. Around 200 million years later, due to the gravitational collapse of hydrogen atom, first star was ignited. This time is known as the cosmic dawn and hence the end of the cosmic dark age. The dynamic of the universe in the dark age is still unexplored due to lack of luminous sources. The 21 centimeter neutral hydrogen spectrum can be a promising probe in understanding the dynamic of the early universe, in particular during this unexplored era. The redshifted signature of the 21 centimeter hydrogen absorption spectrum opens up a new window to understand the process of reionization and the factor of the early universe influencing the same. Thus, the study of 21 centimeter line in reionization era helps in understanding several cosmological and astrophysical aspects regarding the primordial black hole as well as the baryon dark matter interaction, dark energy interaction, etc. in high redshifted epoch. Hydrogen is the most abundant baryonic component of the universe, which occupies around 75% of the entire baryonic mass of the universe. The 21 centimeter hyperfine spectrum is originated due to the transition between two spin states, namely a singlet spin 0 state and a triplet spin 1 state. Energy difference between two hyperfine states, S equals to 0 and S equals to 1, is this expression, and for ground state hydrogen atom, N equals to 1 and Z equals to 1. So the equation takes this form, this second line. And so here ME is the electron mass, that is 0.51 MeV. Mn is the nucleus mass, which is in this case 938 MeV. Gn is the gyromagnetic ratio, which is around 5.56, and alpha is the fine structure constant given by this expression. So this is approximately equals to 1 by 137. So the emitted energy is around 5.84 into 10 to the power minus 6 eV, and the corresponding wavelength is 21.2 centimeter. That's why its name is 21 centimeter. However, we studied the redshifted signal. So what we detected, the detected wavelength is no longer 21 centimeter. That is more than 21 centimeter actually. The experiment to detect the global epoch of reionization signature, or edges, reported a prominent footprint of 21 centimeter line of hydrogen at the cosmic dawn. The cosmic dawn starts when the first star was born at the end of cosmic dark age. Edges estimates the brightest temperature of 21 centimeter spectrum, that is minus 500 millikelvin, at the limit of plus 200 millikelvin and minus 500 millikelvin at a redshift range 14 to 20 with 99% confidence level. But according to the standard cosmology, the estimated brightness temperature is only minus 200 millikelvin. So the additional cooling observed by Edge's experiment can be explained either by enhancing the background temperature or by lowering the baryonic temperature, which is almost equal to the spin temperature at this epoch. I mean Z approximately 17.2 or around 14 to 20. The interaction between baryon dark matter fluid can be such a possible source that cools down the intergalactic medium, resulting in the lower background temperature. Moreover, the evaporation of primordial black hole, dark matter annihilation or decay, and even dark matter dark energy interaction are also possible sources that can modify the global 21 centimeter signal. The brightness temperature basically expresses the intensity of the spectrum. The expression of the brightness temperature of 21 centimeter spectra at different redshift Z is given by this expression. Here, this Ts is the spin temperature, T gamma is the background temperature, and tau, that is function of Z, is the optical depth of the interstellar medium or intergalactic medium at redshift Z, which is given by this expression. Here, A10 is the Einstein coefficient, lambda 21 is the wavelength of the spectra, that is certainly 21 centimeter. Hz is the Hubble parameter. T star is the 21 centimeters temperature, and NHI is the neutral hydrogen number density, and del R del Vr is the radial gradient of the peculiar velocity. Spin temperature Ts is defined as this last expression as a function of cosmic, which basically depends on N0 and N1, that is the number density of neutral hydrogen atom and of singlet spin 0 state and triplet spin 1 state respectively. Spin temperature Ts can also be expressed as a function of cosmic microwave background temperature, which is given by this last expression. Here, this T Lyman alpha and Y Lyman alpha are the Lyman alpha background temperature and corresponding coupling parameter respectively. Using this 21 centimeter signature, we estimated several aspects of primordial black hole in this paper. Here we explored the bounds on pph masses, its abundance, and their variation with different dark matter masses. We also estimate several similar bounds on dark matter mass, which agrees with several recent treatments. In this article, we extend our analysis in the context of dark matter dark energy interaction. Actually, the interaction between dark sector components are still unknown, so we adopt three general standard interaction scenario from the work of Lee et al. And studied several aspects of those models. We also studied multi-messenger analysis of decaying super heavy dark matter, which I already discussed earlier, of the range of 10 to the power 6 to 10 to the power 9 GeV in the context of 21 centimeter signal and the iScope 7.5 year Hesse neutrino data. Oh, I just forget to add the collaborator part. Okay, thank you. That's all.
Thank you very much, Ashadul, for the talk. Now we will look at the audience. Ognideep has a question. Okay, Ognideep is here. Can you ask your question? Your question has three parts, so it's better that you ask your question. Ognideep, you can unmute and ask your question. Okay, I'm not getting any response from Ognideep. So he has asked that can dark matter, first part of the question is that can dark matter be studied in labs and then or by using computation methods, or is it explained theoretically based on observations made using telescopes?
Actually, dark matter can be detected in dark matter detection process is basically there are two methods. One is direct detection and another is indirect detection. Hello, hello.
Yes, you are audible. Ashadul, you are
Yes, sir.
audible.
I think someone is asking some question. That's why I stopped there.
No, 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 just carry on.
Okay. Okay, in the case of indirect detection, we can detect the annihilator decaying particle from dark matter annihilation or decay. Some standard model particles are created, and we detect those standard model particles using radio telescope or other Cherenkov telescope like MES, Major Atmospheric Cherenkov Detection Telescope, etc. And we can using this technique we can detect the dark matter. And certainly computational method is a alternative way, but sorry, ma'am,
In
using
fact, the computational methods are must because we do not know about the nature of dark matter, and
exactly.
one needs to do a computational survey of the various kinds of dark matter models. A whole range of them is there. So that is the most salient method. The 21 centimeter line is proving to be a very useful probe,
In this case
but
we use 21
obviously
radio telescope.
radio telescopes you have to use. And dark matter it cannot be studied in labs because you cannot find it even in the neighborhood of the planetary system at all. But what one can do is one can simulate or one can develop material which has some of the properties of this dark matter using solid state techniques. Such studies have been done. A few studies have been done, and that is actually something we can call analog dark matter techniques studies. Okay, then Shubhadeep Shahu has a question. Shubhadeep, please ask your question. Unmute yourself and ask the question.
Thank you, sir. So, Ashadul sir has explained it very well, sir, in his presentation. And I had a question. Means, what is the difference between this dark energy and dark matter? Although we know from Einstein's famous relation, which we get to know from the childhood days, E equal to mc square, that energy and mass are completely related. So, what is the difference between these two? And sir also pointed out that dark matter doesn't interact with anything. So why did we need to differ these two sections, the dark matter one side and dark energy another side? Thank you, sir. This is my question.
Basically dark dark matter dark energy from several research recent observation it can be seen that the dark sector component is there are two component in the dark sector. One is dark matter and dark energy. In the case of dark matter, it the baryonic barometric that is omega, which I mean pressure by density is 0 like normal matters. But in the case of um, dark energy, that is not like matter, in which exert negative pressure. And this is the basic difference between dark matter and dark energy.
Means it is the dependence on the pressure that
Yes, yes,
is causing
exactly.
us to differ between that dark matter and dark energy.
Exactly. Basically, whatever I told earlier, that is for dark matter, and dark energy. Basically, we can see that this is used to explain the expansion of the universe. If there is nothing with negative pressure, then how the universe is expanding with acceleration? That negative pressure is coming from the dark energy.
Okay, sir.
It
Then,
is
then, sir, I
everything
got to
is
know from.
just approximation, or actually nothing is observed directly. Although dark matter can be some dark matter particle can be um, observed using direct detection method. In this case, dark matter candidate hit with the standard model particles and produce some other standard model particles which can be detected. Other standard model particles basically means electrons and muons. Using those detecting those muons and electrons, the existence of the direct detection method of dark matter was carried out.
Thank you, sir. But sir, means we had from the Red Sea experiment, sir, we got to know that universe is expanding, but we don't know what is going to happen next. Whether it is going to expand and expand like that, or whether it is going to means after a certain time, after a peak point, it is going to contract. Means after that, do we have something to propose that yes, this is going to contract, then we will have a big crunch like thing, another Big Bang will follow it.
According to normal cosmology, since normal cosmology, universe will expand with acceleration, so it will never contract. But there are several other models which supports that the conjecture of Big Crunch. But a standard cosmological model does not tell us that. But actually,
Okay,
nobody have the actual idea, because we don't know what will happen.
okay, sir. Thank you, sir.
Actually, to continue a little bit on Shubhodip's question, that the difference between matter and energy, one says that these are equivalent forms, and obviously you can
Oh,
do a change of scale. But we understand matter in this context as being that stuff which was non-relativistic at the time of decoupling, and energy as the stuff which is relativistic at the time of decoupling from the expansion. So that is the primary difference here. Apart from, and you can obviously, as Ashadul has pointed out, you can look at the equation of states to find out what kind of matter. That is, suppose we have iron and you have gold. Both are matter, both are equivalent to energy. Both are not same. They have different nature. So similarly, dark matter cannot be, for example, baryonic. It is collisionless. So it has a certain characteristics. Dark energy has different characteristics, both efficiently expressed in terms of equation of states. And about these alternate cosmologies, which Asharul has pointed out, whether the standard cosmology is based on observations at the current time with the current level of precision, which are considered to be very high at the current point of time. And from the Friedman model tells us that well, the universe is going to expand. Its rate of expansion is going to expand, and so on. But obviously, when one improves the observation or one takes into consideration of several other factors that suppose how the universe itself came into being and so on, whether there are multi-universe objects, then other cosmological pictures also can be considered, and many of these big crunch and other models all are accommodated within simple Friedman models. So the standard cosmological model is based on the measured values of the standard cosmological parameters. Universe described essentially in two numbers, the Hubble's constant and the deceleration parameter. Okay. Then I see here that Omega DS has a question. Okay, Omega DS, can you unmute and ask your question?
Yes. Do cold and hot dark matter impact gravitational lensing differently?
Certainly, cold and dark matter. Actually, that depends on the when any dark matter collapse under gravity. The lensing effect basically proportional to the mass of the lensing bodies. That doesn't depends on types of dark matter. If the lensing bodies is mediated with or the condensation of cold type dark matter or hot type dark matter, it doesn't exert any effect on the lensed image.
Thank you.
In fact, it is more probable for cold dark matter to be the lens and the hot dark matter to be the rays which would pass and would get lensed. So different roles, like hot dark matter, maybe the neutrinos or whatever, they would get lensed, and the cold dark matter would sit down there as ducts like cold lenses. Okay. Any other questions?
So I have one question. May I ask
Yes,
directly?
yes,
Yes,
Aditya,
ma'am.
please go on.
Yeah. And so I just wanted to know this. So this hot dark matter, cold dark matter, it depended. It was classified with respect to the velocity, right? Means
Yes, ma'am.
velocity of dark matter during Big Bang. That's what you were saying.
Yes, ma'am.
So,
No,
so
not
in
during Big Bang.
No, during structure formation.
during structure formation. Okay. So when this dark matter is formed at that time, what is the velocity, right? So that velocity depended on a mass according to the expression that we were seeing, correct? The mass of the dark matter.
Uh, um,
No,
deep
basically,
velocity.
see, Aditi,
Huh.
suppose we are thinking about different candidates as being the dark matter. Now, what can be these hot dark matter objects which are relativistic? Those could be, for one example, is the neutrinos. But
Okay.
the neutrinos would be hot because they have their full energy is kinetic, and so on. However, these objects, since these are highly relativistic, they would not be efficient for the formation of structures. On
Oh,
the
okay.
other hand, the cold dark matter, they would be able to create inhomogeneous and accrete matter around themselves, so that the scale of fluctuation, which is like 10 power minus 5 in the CMB, actually it needs a little bit more. So those would have to be sitting ducts which could absorb, which could accrete matter around themselves, forming inhomogeneities, which would subsequently develop into structure. So there are two structure formation scenarios, in one in which the bigger structures forms first and one in which the lesser structures forms first. So initial arguments showed that so if one of the two scenarios have to be adapted, and that ousted out the hot dark matter scenario for so quite some time. Now it is coming back because of various reasons. But basically, hot dark matter it consists of very relativistic matter, which by themselves are not able to form structure much. It's very hard to confine them.
Okay. So I got it a little bit now. That mass that we are talking about there in
Yeah,
the structure formation. So how is that? Means is that estimated through? Then how does one know that what is that mass?
that comes from the theory of structure formation. Okay, that how much inhomogeneity you need comes from a quantity called the density contrast. What kind of density you need around an inhomogeneity, so that the inhomogeneity will become will be able to acquire more mass compared to its surroundings. In the
So,
other case, what will happen is that inhomogeneity would dissolve, and one compares the inhomogeneity with the inhomogeneity observed in the CMB, which is otherwise very inhomogeneous, but which has little signatures of inhomogeneity, and compares the two to find out what the initial sizes of the structure formations could have been.
okay, okay. Thank you, sir. Thank you.
Okay, so if there are no other questions, I want to thank the speaker once again, and this discussion would come to an end. I would like to thank everyone who has who has conceived this idea, our HOD, who has conceived this idea of interaction between the frontiers of research and who are will be actually going for research afterwards, the support of the college, all the faculties, the students and the staff, and obviously the speaker himself. So with these words, this little event is brought to an end. Thank you very much for your participation.
Just one correction, Professor Banerjee, that this is not my concept. This is the concept of the department, that there should be an interaction between the students and the faculty
Of
members,
course.
and there is a collective thing. So thank you, Ashadul, for a fantastic talk.
Thanks.
It's really wonderful to listen to you, and we are proud of you because as you are the first PhD student of
Thank you, sir.
department, and hope you will have a very bright future. And I thank all of you, Professor Banerjee, for conducting this technical session so nicely. So I think that of course today was a entire we have a offline class day, so that is why a little bit of students those have told me that they are basically on the just they have classes up to 4 p.m. So from next colloquium we are going to shift this time because it was scheduled earlier, but it's recorded. I think Ashadul, you can send us this record, right? This is recorded,
Yes,
so
sir.
those
Yes,
who
sir.
want, I can give them the record of this talk, and in future in online as well as offline mode, whatever is possible and suitable for us, we'll continue this lectures. So next lecture I'll let you know as soon as I confirm with the speaker. Already I've talked with the speakers, so I'll just confirm you the date, and I request you so that in the future also you come with your students, and that we have a very good discussion in the forum. Thank you all.
Or
Thank you very
we
much.
can actually upload these talks to the YouTube.
Okay, sir.
Right.
We have an YouTube channel.
রাইট রাইট প্লিজ আশাদুল প্লিজ সেন্ড মি বিকজ ফার্স্ট ইয়ারের অনেকেই আজকে আমাকে বললো যে স্যার আমরা 4টার সময় বেরোচ্ছি, আল্লাহ ডোন্ট ওয়ারি, আই রেকর্ড ইট। তার কারণ এটা ডেটটা আসলে আমাদের টাইমটা অনেক আগেই ফিক্স ছিল। ঠিক আছে, আমরা নেক্সট
ছুটি
টাইম
হয়ে গেলে
থেকে
তো
একটু
আমাকেও হোস্ট করতে হতো না। রূপমই করে
একদমই
দেবে বলেছিল।
একদমই তাই, একদমই তাই। তো
আমি আপলোড করে দেবো স্যার।
ফ্যান্টাস্টিক। ওকে, তো থ্যাংক ইউ অল, থ্যাংক ইউ ভেরি মাচ।